On we go, question 4. Please do take a minute to pause this video and try the question before we go through it. Okay, we've got a simplified roulette wheel. And there are only 3 possible numbers on it, 3 possible sort of sections on the wheel. They don't take up equal amounts, so the one labelled with 1 is half the wheel, and so on. And 5 is 120 degrees and 10 is the rest, the remaining 60 degrees. So let's talk about this little table here. I might draw it again a little bit larger, so I can write in it. So what you have is this, it's quite a funny way of laying it out. X represents a number, and in this case X can either be 1 or 5 or 10, and what you have on the second row is the probability, that's that capital P, that the score is equal to X. So to find out what I should put in this box here, I asked what's the probability the score is 1, and I think that should be half of the wheel, 180 degrees out of 360. The chance you get a 4 is 120 degrees out of 360, that's a third, and the rest, well, I guess you can either think of this as the rest of the circle is 60 degrees, so 60 out of 360 is 1/6, or possibly the probabilities here have to add up to 1. They sum up to 1 in total, because one of those 3 outcomes is all that we're allowed. Okay, so now we spin the wheel n times, some large number n. So we'll do score and frequency. We'll make a new table. 1, 5, and 10. So I think I would roughly expect roughly half the outcomes to be 1, roughly 1/3 of the outcomes to be 5, and roughly 1/6 of the outcomes to be 10. So that's n over 2, n over 3, and n over 6 is what I would expect. So let's look at the average score, the mean of these things, in exactly an analogous way to what we did. We would get the following calculation. I'll do it in blue. 1 times the number of them, which is n over 2, plus 5 times n over 3, plus 10 times n over 6, and all of that would then be divided by n. Now, this is a sort of pretty nasty triple-decker fraction-y type arrangement. I'm going to rewrite this compound fraction in a new way. I'm going to write this as... Actually, no, I think I should be okay. I'm going to divide each of these terms, okay, terms separated by the plus signs, by n. That's what I have to do with this n on the bottom. How do I divide n over 2 by n? I think I just get a half. So I would get 1 times a half plus 5 times a third plus 10 times a sixth. Not divided by anything anymore, just as it is. So we're getting 1 times the proportion of the outcomes we think is 1, plus 5 times the proportion we think is going to be a 5, plus 10 times the proportion of the outcomes we think is going to be 10. So what's interesting here is the n dependency disappears. I'm actually going to put in a common denominator of a sixth. So I think I get 3 over 6 plus 5 times 2 over 6, which is 10 over 6, plus 1 over 6, which I guess is 14 over 6, which I could simplify down to 7 over 3. So if you have a large, or you'd expect the average of your rolls to be 7 over 3, and also you would expect that if n were very large, this would become more and more accurate. So I'd just like to draw your attention to, I think, the obvious. What you have here is the scores multiplied by their corresponding probabilities now. So in our calculation up here, we had kind of the number of ones we expected divided by the total number of rolls, of spins. That's the proportion of the spins we expect to be 1, and that's the same as the probability of getting a 1. Okay. Variance, a little bit trickier. I'll do it with the n's again, so I'll do it using the table in black, and the slogan, mean of squares minus square of means. Well, I'll get rid of that, that's not helpful. So, what does that mean? How do we do that? Well, I guess we do 1 squared times n over 2, plus 5 squared times n over 3, plus 10 squared times n over 6, the number of those, minus the mean squared. And the mean we expect is just 7 over 3. So I'll just do that as 7 over 3, sorry, 7 over 3 squared, like that. Okay. I've done something wrong. What I've done here is the sum of the squares. I want the mean of the squares, so I better divide that by n. Okay, so this is the variance. I'll put var there. And again, I can split the fraction up and divide the n over 2 by n to get 1 squared times a half plus, maybe I won't write that as 1 squared, I'll write that as 1, so we can cope with that. 1 times a half plus 25 times a third plus 100 times a sixth. Okay. I'm going to use a common denominator of a third, of a sixth here again. Sorry, minus 49 over 9. So that's 3 over 6 plus 50 over 6 plus 100 over 6 minus 49 over 9. I think I actually need a slightly different common denominator, probably an 18th. So I get 153 over 6, which is 459 over 18, subtract, 98 over 15. Not particularly good, 18, not a particularly good 98, but you'll cope. And that is equal to 361 over 18. Okay, so that's the variance. The variance here is roughly 20. So the standard deviation we would expect, although we're not asked for it, roughly, I don't know, 4 and a bit, 4.4, something like that. So let's look at the original numbers and make sure that makes sense. That says we expect most, but not all of the numbers to be within 4 and a bit of the average. Okay, so 4 and a bit of the average includes the 1 and the 5, so that is, I think, a believable answer for the variance. But the answer to the question is that the mean, just summarise it at the bottom, the mean, the expected mean I should say, is 7 over 3, and the expected variance is 361 over 18.